This is physicist Peter Higgs, and he's barely holding back tears. It's CERN 2012. His colleagues have just announced the discovery of a particle without which one of the most fundamental questions in modern physics could not be answered. Where do elementary particles get their mass from? Half a century earlier, Higgs had mathematically predicted that such a particle must exist in physical reality. Without it, even atoms wouldn't form. The Large Hadron Collider, one of the most ambitious scientific projects in history, was built to find that particle. But if the Higgs boson gives mass to all other particles, then where does it get its own mass? Is it made up of something even deeper? The energy levels used in those earlier collisions weren't high enough to probe further. So what did scientists do? They tore it down. This system of superconducting magnets, sensors, and vacuum pipelines stretching through a 27-kilometer tunnel beneath the border of France and Switzerland was almost completely rebuilt. Expensive, time-consuming. It took 3 years of upgrades, calibrations, and reboots, thousands of physicists, engineers, and administrators, all for the sake of unlocking the next layer of fundamental physics. In 2016, the Collider was reborn. Its collision energy was increased by 50%, detector precision and luminosity dramatically improved, meaning far more frequent particle interactions. And then, silence. No new fundamental particles have been discovered since. On the 10th anniversary of the Higgs discovery, Science magazine published an ominous headline. 10 years after the Higgs, physicists face the nightmare of finding nothing else. And University of Chicago physicist Juan Kohler put it bluntly, if nothing else is found at the collider, particle physics is over. He's not talking about next year. He means the next 15 years. 15 years of sifting through data, running experiments, and hoping for something that will push physics forward. Because if you look at what the Nobel Prize in Physics has recognized in the last 2 decades, nearly all of it celebrates work from the 1970s and 80s. So maybe the problem isn't just the collider. In a recent interview, the new head of CERN expressed just how much hope is now being placed in artificial intelligence. Not coincidentally, the Nobel Prize in Physics was recently awarded for contributions to machine learning. AI is now being woven into the operations of the Large Hadron Collider with increasing sophistication. Mark Thompson, not without pride, notes how machine learning is shaping the future of discovery. This all unfolds as scientists debate the construction of an even more colossal collider, 3 times the size of the current one, spanning 90 kilometers in circumference and costing at least double. But this time, the breakthrough isn't expected from a brilliant theorist. It's expected from machines, from tools, from algorithms that might finally illuminate a path forward where human reasoning has stalled. And that's why skepticism is growing louder within the scientific community. Some criticize openly. Others pose the questions more delicately. Are we sure we're heading in the right direction? Is this really the way forward? One of the scientists who helped discover the Higgs boson, Bruno Mansoli, has recently released a book titled Physics in Crisis, From Multiverse to Fake News, and in it, he delivers a sharp and honest assessment of modern physics. He writes, "A theory should be considered false as soon as at least one of its predictions has been disproved by experiment or, in the case of astronomy, observation." So why? Haven't we rejected the standard model or general relativity? The first reason, we don't have anything better. Nothing that works as well, nothing with fewer contradictions. The second, we've patched the holes. We've invented placeholder concepts to account for what we don't understand, like dark matter and the even more mysterious dark energy. But this, Mansoli argues, isn't the real crisis. The crisis is that the further we look, the more uncertain it becomes that anything better will ever come along. That pessimism is echoed and amplified by physicist and outspoken critic Sabine Hossenfelder. She argues that large swaths of physics have stalled, and that researchers, desperate to appear productive, are churning out meaningless or even absurd papers on an industrial scale. They're mimicking progress because the alternative might be irrelevance. Here's what that looks like in practice. In 2015, at the Large Hadron Collider, 2 massive collaborations, each involving hundreds of scientists, announced evidence of a possible deviation from the standard model. It was something no one had predicted. For a moment, it looked like physics was about to explode. But 6 months later, it turned out to be a statistical fluctuation, a computational error. And in that short time, more than 600 papers had already been written. Some were published in top-tier journals, yet none of them described reality. They were built on noise. And Hossenfelder says that's the real problem. Not that mistakes happen, but that the system rewards rapid, flashy publication over genuine understanding. In the race for citations, even real science gets hijacked by the pressure to publish first and ask questions later. This pressure has led to another growing concern, one that few expected to hit physics: the reproducibility crisis. We tend to think of physics as solid, rigorous, immune to the replication issues plaguing psychology or medicine. But it turns out the problem runs deep, even in the most precise sciences, even in condensed matter physics. An entire international conference was recently held to address this very issue. The researchers themselves admitted that too many studies are being published without sharing the raw data, and that leaves readers with two bad options: take the results on faith, or try to reverse engineer the inconsistencies from the incomplete picture they've been given. Scientific publications with serious inconsistencies don't disappear quietly. They often linger in circulation for years before finally being retracted, if they're retracted at all. In that time, they remain part of the academic ecosystem. They can still be cited, still shape discussions, still influence future work. And the job of cleaning up this academic forest, of keeping the scientific record accurate, is becoming harder, slower, and vastly more expensive. Even staying up to date with one's own field is becoming overwhelming. The rate at which scientific articles are being published is increasing exponentially, and yet even prestigious journals like those of the American Physical Society are publishing studies with little to no raw data to back them up. Sometimes they'll even include a disclaimer: yes, there's no data, just keep that in mind. That's exactly what happened with a recent paper from Microsoft's quantum computing team, and it was published anyway. These are just the tip of the iceberg, admitted the co-organizer of a recent international conference entirely devoted to the reproducibility crisis in physics. They're not the cause of the problem, they're just the stories we happen to notice. Behind the scenes, a less visible issue makes this problem worse: the competition for grants, and the way grant systems affect scientific motivation. In some parts of the world, such as the post-Soviet space, grants are a crucial supplement to researchers' salaries, which means the pressure to win grants isn't just about the science, it's personal. It can become a matter of survival, and when funding becomes a proxy for your livelihood, the temptation to exaggerate your results increases. Elsewhere, such as in the US, Europe, or China, grant structures typically work differently. Salaries are covered by universities or research centers, and grants are earmarked for conducting specific projects, buying equipment, funding experiments, travel, and publications. In these systems, the motivation to secure grants tends to be more professional than personal. But here's the catch: science doesn't always yield results on demand. You can spend a year or several working tirelessly and still come up short. Yet funding systems demand results, not just results, visible ones, preferably ones that make headlines. And so, some researchers begin to stretch the truth. They oversell the importance of their work. They inflate the significance of their results. Press releases sparkle with language about breakthroughs and revolutions that in reality may never materialize. This doesn't just create the illusion of progress, it creates the illusion that the scale and impact of scientific advances are far greater than they really are. And this illusion helps mask the deeper stagnation of physics from the public. Because from the outside, it still looks like the field is thriving. New theories, massive experiments, one dazzling announcement after another. And yes, applied physics, unlike its fundamental counterpart, continues to deliver. It's not trying to solve the mysteries of the universe. It's building things, new materials, better data storage, more efficient energy systems. These innovations are real and tangible, often entering our daily lives within a few years. But most people don't distinguish between applied physics and fundamental physics. They see headlines about billion-dollar experiments like Dune, a massive neutrino hunting project, and they assume it's all part of the same forward march. The official promise of Dune? To help answer why matter even exists, why the universe didn't cancel itself out at birth. But in the retelling of pop science blogs and flashy documentaries, it becomes something even bigger. Why does the universe exist at all? Why are we here? As Sabine Hossenfelder bluntly notes, no matter how impressive Dune's results might seem, even if it delivers something unexpected and groundbreaking, it still won't answer the core question. Why is there more matter than antimatter in the universe? Because that question isn't just hard, it's unanswerable, at least within the framework of our current physical theories. It sits entirely outside the boundaries of the standard model, and experimental data by itself is meaningless. It's like a set of lockpicks with no lock, useless without the right theory to open anything. Data needs context. Otherwise, it's just noise. That's when I had a hard realization. We, science journalists, communicators, even well-meaning popularizers, are part of the problem, whether we intend to or not. We report breakthroughs, cite impressive-sounding numbers, amplify research, and use metaphors to make it all digestible. But how can we accurately assess what's groundbreaking and what's just academic fireworks, when the very experts within these fields often remain quiet? Scientists rarely call each other out in public. It's not part of the culture. Criticism, if it exists at all, is reserved for behind closed doors, for technical papers or formal rebuttals, and always under strict internal rules of conduct. As a result, entire areas of research can dominate headlines, shape funding, and define popular perception, without producing any experimentally confirmed results. No observations, no reproducible data, no working models. And yet, theories like string theory and supersymmetry continue to float atop the media wave, collecting prestige, attention, and public curiosity. Let's not forget, in the early 2000s, John Horgan, a respected American science journalist, placed a $1,000 bet with theoretical physicist Michio Kaku, a superstar in the world of science popularization. The bet that no Nobel Prize would be awarded within the next 20 years for achievements in string theory or any other grand unified theory of everything. Horgan won that bet. That was 6 years ago, and things haven't changed. No Nobel for string theory, no grand unification of the fundamental forces, just models. Elegant, bold, but still speculative. At this point, you might be asking, why am I saying all this? Am I trying to depress you? Disillusion you? Drive you into some kind of existential crisis about physics? The very foundation of objective knowledge about the universe? No, that's not my goal. I just couldn't ignore it any longer. This quiet tension has been gnawing at me for years, and I needed to confront it. What is really happening with physics today? And perhaps more importantly, how do we protect ourselves from those who exploit science's growing pains to peddle even worse nonsense? How do we separate valid criticism from veiled attempts to replace reason with superstition? And studies show a disturbing trend. Even in wealthy, educated countries, trust in science has taken a hit, especially after the pandemic, not just in biology or medicine, across the board. And physicist Etienne Klein believes the root of the problem is something surprisingly simple, yet deeply misunderstood. We confuse science with research. To most people, they sound interchangeable, but they're not. Science is about answers, definitive, tested, consensus-backed conclusions that are hard to dispute. It gives precise responses to precisely posed questions. And, as Klein says, these answers cannot be challenged on the basis of perception, imagination, or the senses. But research, that's something entirely different. It's the pursuit of what we don't know. It's an engine of uncertainty. Research, Klein adds, is the doubt that comes from the realization that we don't know something. This doubt comes from knowledge, not ignorance. During the pandemic, the public got a front-row seat to real-time scientific research, disagreements, revisions, and uncertainty. But because many people mistook research for science itself, they began to doubt the validity of science as a whole, and that confusion has been hard to shake. This is exactly why talk of a crisis in physics has begun to drift out of academic journals and into the broader culture. And that's dangerous, because without context, it's easy to misinterpret what physicists are actually worried about. So let's get that context right. According to physicist Bruno Manzoli, who spent decades working at CERN, the fundamental crisis in physics is this. We've reached the limits of two pillars that used to seem unshakable. On one side, the Standard Model, which governs the infinitely small atoms, subatomic particles, the very building blocks of matter. On the other, general relativity, which explains the infinitely large, stars, galaxies, the fabric of space and time. The Standard Model is built on two 20th-century breakthroughs, quantum theory and special relativity. Together, they form a mathematical masterpiece, so accurate it can predict the magnetic moment of an electron down to 1 part in a trillion. Every lab measurement ever made agrees with it. It's consistent across all types of particle accelerators and energies. Despite its underwhelming name, the Standard Model is the most successful theory we have about the fundamental workings of nature. Meanwhile, general relativity, born from Einstein's insights, perfectly explains gravity on every scale, from planets to satellites to the warping of space-time itself. It predicted black holes before we could ever see them. It predicted gravitational lensing, which we've now observed with precision telescopes. So what's the problem? The problem is that these two brilliant theories, one for the quantum world, one for the cosmic, don't work together. They sit side by side, but when you try to apply both at once, say in a black hole or at the beginning of the universe, everything breaks down. Insoluble paradoxes arise, writes Manzoli. Try using general relativity to describe the quantum world and the whole thing breaks down. The math falls apart, the predictions become meaningless or can't be made at all. Because these situations require you to consider both quantum effects from insanely high energy densities and gravitational effects from massive objects at the same time. And we simply don't have a theory that can handle both, not yet. This is why it's so concerning that even within the field, more and more hope is being placed on tools, colliders, AI systems, bigger experiments, rather than on new theoretical approaches. These tools are powerful, yes, but it seems that they initially ignore the root of the problem, the fundamental problems with the theory. For decades, physicists have chased so-called theories of everything, unified frameworks that could reconcile general relativity and quantum mechanics. Some, like string theory and supersymmetry, have gained near-mythical status, but they've failed to produce experimental confirmation. And yet, we're still building careers on them. Why? Because, as theoretical physicist Sean Carroll himself admits, even while arguing there is no crisis in physics, there's a problem with the culture of science itself. In his 4-hour podcast monologue defending the state of modern physics, he acknowledges that the field has become risk-averse. It's dangerous to step off the beaten path. Write a bold, unconventional paper and you risk rejection. Pursue a fresh line of thinking and you might get labeled a crank. It's not just about facts and formulas. There's a very human social pressure within the system. And this brings us to the psychological side of the crisis. Science is still a human endeavor. Scientists aren't perfectly rational algorithms. They're people, navigating careers, reputations, funding politics. Sure, we have safeguards, peer review, professional standards, institutional prestige, but those structures can't always overcome human nature. Physicist and outspoken critic Sabine Hossenfelder puts it bluntly. Many physicists have retreated so far into abstract mathematics that they've lost touch with physical reality. The result? A widening gulf between theorists and experimentalists. In Hossenfelder's view, this is partly practical. It's simply easier to build a career in theoretical work, and theories like string theory and supersymmetry, despite decades without a single experimental confirmation, remain popular, partly because they're beautiful, elegant, clean. They look right. Almost like Einstein's theories once did. But that, Hossenfelder warns, is exactly the problem. In her book, Lost in Math, she argues that we've become seduced by mathematical beauty, and now we treat it as a substitute for truth. And when you do that, you stop looking around, you stop questioning, you stick to the script. And so, despite our tools, our intelligence, and our ambition, we're standing still. So what do we do now? How do we move forward from here? Let's go back to the late 19th century, just before physics turned upside down. A common myth says that Lord Kelvin once declared physics was done. The basic principles have been established, the quote goes. All that's left is to measure to the 6th decimal place. Except, it wasn't Kelvin who said it. That was actually Albert Michelson, fresh off his groundbreaking experiment showing that the speed of light is constant, a result that quietly shattered classical mechanics. What Kelvin actually said was more poetic and far more prophetic. The ultimate success of physics in understanding nature is overshadowed by two small clouds. The mystery of the ether, the supposed invisible medium through which light travels, the inability of classical physics to explain the spectra of atoms, despite having predictive success elsewhere. At the time, those were seen as minor inconsistencies, but as physicist Bruno Mansoli notes, they turned out to be thunderheads. Within a few decades, experimental discoveries, X-rays, radiation, the photoelectric effect, blew open the walls of classical physics. The result was a scientific revolution. Quantum theory, relativity, a complete rewriting of our worldview. And yet, that revolution wasn't driven by theory alone. It was the perfect storm. Precise measurements showing cracks in the model, new mathematical tools like linear algebra and curved geometry, experimental breakthroughs from photography to early electronics. Today's physicists dream of living in such a moment, but now we've done most of the easy experiments. We've measured everything we can with incredible accuracy, and the new questions require monumental resources, massive colliders, vast data sets, global collaboration. It's harder than ever to justify those investments without showing success from previous efforts. Today's two small clouds are different, but eerily familiar. Dark matter, dark energy, the incompatibility of general relativity with quantum mechanics. They linger over modern physics just as Kelvin's clouds once did. But maybe the reason we're stuck is that we're waiting for the wrong kind of revolution. The kind Thomas Kuhn famously described, where paradigms collapse and a new framework takes over. We abandon geocentrism to understand planetary motion. We let go of rigid notions of space and time to build quantum theory. So, what is it we must abandon today? One idea, our obsession with linear thinking. Physics has long leaned on linear equations. They're elegant, solvable, and predictable. But real-world systems are often nonlinear, especially near points of radical change. Take phase transitions, like water turning to ice. A tiny drop in temperature creates an entirely new structure. It's not just the individual molecules, it's their collective behavior. At that tipping point, even distant atoms influence each other. Linear tools fail to describe this, so maybe the way forward isn't just bigger colliders or flashier math. Maybe it's about finding new types of thinking, mathematical frameworks that embrace complexity, nonlinearity, and emergence. Because sometimes to see the universe differently, we don't need a new tool, we need a new lens. Even the most radical ideas in theoretical physics often remain trapped within the same old method. Take non-commutative geometry, for example. It's a theory where we abandon the classical idea of space as points and lines and instead describe everything through functions. Abstract constructs that let us infer where things are without needing to define where, the same way we always have. And yet, as physicist Bruno Mansoli points out, even this bold framework still follows the familiar rhythm. A theory emerges from human imagination. It's formalized mathematically. It's compared to experimental data. That process hasn't changed since Archimedes measured water displacement in his bathtub. From ancient levers to the Higgs boson, physics has always followed this loop of observation, interpretation, validation. Sure, today's theories are deeper, the math is more complex, the instruments are much bigger and more precise, but the underlying method remains the same. This is still how we teach physics students, and this is still what we expect of them when they enter academia. A well-oiled system that's not exactly built for creative disruption. Even Manzoli, who helped lead the discovery of the Higgs, admits it. There's not much room for nonlinear thinkers in academia. The conveyor belt doesn't reward rebellion, it rewards mastery of the known. And that raises a crucial question. Why would we expect revolutionary new thinking to come from a system that's not designed to encourage it? This doesn't mean the education system is broken. A budding physicist should know their physics, not just poke holes in it from a place of ignorance. But it does mean the ground beneath us, our mathematical assumptions, our cultural structures, our expectations, might be overdue for an upheaval of its own. And here, it's tempting to invoke artificial intelligence. Surely if humans can't break through, machines will do it for us, right? That's a comforting idea, but maybe too comforting. Maybe AI as a savior is just another version of the philosopher's stone, a lazy belief in a magic wand. Because no matter how powerful the tool, what good is a theory of everything if we can't even understand it? Physicists have been joking for a century that no one really understands quantum mechanics. What makes us think we'll suddenly grasp a deeper theory just because a machine hands it to us? The truth is, revolutions in thought have always come from human insight. Natural intelligence, not artificial, has always been the engine of transformation. So maybe the real question isn't, when will AI solve physics? Maybe it's, are we, humans, ready to think in ways we never have before? Thanks for watching, friends. Every action you take, whether it's a like, a comment, or a subscription, keeps this project alive. I feel that support. Thank you for being here. And if you want more, help support the channel. It truly matters.